Let's summarize what we've learned about refraction, especially in the wave model. Number one, we know that the frequency of light stays constant in all media, because otherwise the light waves would pile up on one side of the interface. That can't happen. Number two, the effective speed of light in a vacuum, in a medium, is always less than the speed of light in a vacuum. By definition then, the index of refraction is equal to 1 in a vacuum and is always greater than 1 in other media. That means that light always travels slower in anything but a vacuum. As light passes into a medium with a greater index of refraction, its speed decreases and its wavelength also decreases. As light enters a new medium, it will bend towards the normal to the surface of the medium that has a higher index of refraction. And finally, the path of light as it travels from one medium to another is described by Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. There was a third phenomenon that Newton explored, and that was dispersion. That is, that we can see that light is made up of colors. When light is passed, white light is passed through a prism, it refracts twice. Once as it passes from the air into the glass, and then again as it passes from the glass back into the air. As a result, we find that different colors emerge. Why would that be? Well, the only possible reason is that the index of refraction must vary with the color of light. It shows that the red light has a lesser index of refraction than, say, violet light. The violet light bends more towards the normal. Newton explained this by saying that light particles of different color actually travel at different speeds. And of course that means they have different indices of refraction. So as n varies, so does the deflection from the normal line to the surface. Well, Newton's theory basically said light particles with different colors travel at different speeds, but that doesn't tell us a great deal. It just tells us that different colors are in some way different, but it doesn't actually quantify it. The wave theory, however, provides a clearer relationship. What we can see is that as wavelength increases, the refractive index decreases. The index of refraction of a material varies somewhat with the wavelength of light. That is, each color has its own different wavelength. If we look at these different materials, you can see these curves that show the changes in refractive index with wavelength. And we'll talk about what these wavelengths are relative to color, but this band here represents going from violet essentially to red. As a final note, we can see that dispersion also explains rainbows. In the picture on the left, you can see light hitting a water droplet. The water droplet acts very much like a prism. The light on entering the water will travel at different speeds according to wavelength. And consequently, when they emerge from the droplet on the other side, they've been dispersed. They've been separated, and hence we see the many colors of the rainbow. Well, all of this, reflection, refraction, dispersion, they're all explained, as we saw, by both Newton's particle theory of light And we've also seen them explained by Huygens' wave theory of light. So, which one is it? Which theory best explains what's going on, the particle theory or the wave theory? In the next section, we're going to focus on a couple more phenomena and try to explain those, and perhaps get some insight into which theory is more likely correct.